Hello, and welcome. Today we're going to tackle a fascinating engineering problem that delves into the core principles of rotational motion and forces. By the end of this video, you will be able to analyze the forces acting on a specific rotating object and determine if it can generate enough lift to overcome gravity, based on fundamental physics principles. The specific device we've been asked to analyze is a unique one. Imagine a 2-meter-long plank of spring steel, curved at a 30-degree angle, with aerodynamic weights at each end. This entire assembly is spun by an electric motor at a blistering 10,000 revolutions per minute. The core question is this: can the centrifugal forces generated by this rapid spinning be harnessed to lift the entire apparatus, including the motor driving it, off the ground? To answer this, we'll need to explore concepts like centripetal force, angular velocity, and Newton's laws of motion. Let's dive in. First, let's clarify the forces at play. When an object moves in a circle, it's constantly changing direction, which means it's accelerating. According to Newton's first law, an object wants to travel in a straight line. To force it into a circular path, a force must be applied that constantly pulls it toward the center of the circle. This center-seeking force is called the centripetal force. It's a real force, provided by things like tension, gravity, or friction. You've likely also heard of centrifugal force. From the perspective of the spinning object, it feels like it's being pushed outwards. This apparent outward push is what we call centrifugal force. It's important to understand that in a stationary or inertial frame of reference, centrifugal force isn't a real force. It's simply the effect of the object's inertia, its tendency to continue in a straight line. For our analysis, we will focus on the real, measurable forces, starting with the centripetal force. The magnitude of the centripetal force can be calculated with the formula F_C equals m times omega squared times r. Here, m is the mass of the rotating object, r is the radius of its circular path, and omega is its angular velocity, which measures how fast it's rotating. Now let's apply this to our specific device. We need to define our parameters and do some calculations. First, let's convert the rotational speed into the units we need for our formula. The motor spins at 10,000 RPM, or revolutions per minute. We need to convert this to angular velocity, omega, which is measured in radians per second. First, we convert revolutions per minute to revolutions per second by dividing by 60. This gives us about 166.67 revolutions every second. Next, since there are 2 pi radians in one full revolution, we multiply by 2 pi to get our angular velocity. This gives us an omega of approximately 1047.2 radians per second. This is incredibly fast. Next, we need to estimate the mass of the components. We'll need the density of steel to calculate the mass of the plank. The density of steel is about 7,850 kilograms per cubic meter. The plank's volume is its length times width times thickness, which is 0.003 cubic meters. Multiplying these gives a mass for the plank of about 23.55 kilograms. Let's assume the aerodynamic weights at each end are substantial, say 5 kilograms each, for a total of 10 kilograms. With our angular velocity and mass, we can now calculate the centripetal force required to keep just one of the end weights moving in a circle. Let's calculate the centripetal force on a single 5-kilogram weight. We'll use our formula, F_C equals m asterisk omega squared asterisk r. The mass m is 5 kilograms, omega is 1047.2 radians per second, and the radius r is 1 meter, since each weight is at the end of the 2-meter plank. Plugging in the numbers, we get 5 times roughly 1.1 million. This results in a staggering centripetal force of approximately 5.5 million newtons. This is an enormous force, equivalent to the weight of over 550 metric tons. This force must be provided by the tension in the steel plank. The plank itself is pulling the weight toward the center. Now for the most important part of the question: can this generate lift? The key is the 30-degree curve of the plank. Let's assume the ends of the plank are angled upwards at 30 degrees relative to the horizontal plane of rotation. The tension in the steel arm, which provides the centripetal force, will therefore also be angled at 30 degrees. We can break this tension force down into 2 components: a horizontal component that acts as the centripetal force, and a vertical component that could produce lift. The horizontal component of the tension must be equal to the centripetal force we just calculated, about 5.5 million newtons. The vertical, or lift, component is what we're interested in. It can be found by taking the centripetal force and multiplying it by the tangent of the 30-degree angle. Calculating this for one weight, we get a lift force of about 3.16 million newtons. Since there are two weights, the total theoretical lift force is double that, or approximately 6.3 million newtons. That's an incredible amount of upward force. So we've calculated a massive upward force. The next logical step is to compare this lift to the total weight of the machine to see if it can get off the ground. Our calculated total lift is over 6 million newtons. Now let's find the total weight we need to overcome. The total mass is the sum of the plank, the weights, and the motor. Let's estimate a heavy-duty motor at 50 kilograms. This gives a total mass of about 84 kilograms. To find the weight, we multiply the mass by the acceleration, due to gravity, 9.81 meters per second squared. This gives a total weight of only about 820 newtons. Comparing the two, our calculated lift of over 6 million newtons is vastly greater than the 820 newton weight of the apparatus. Based on these numbers alone, it seems like it would not only lift off, but launch into orbit. However, this is where a theoretical calculation meets the harsh realities of physics and material science. We need a reality check. Before we conclude, we must consider two critical, real-world constraints that our simple model ignored. First, let's consider the structural integrity of the steel plank. Can it actually handle these forces? The total tension in each arm is about 6.3 million newtons. The cross-sectional area of the plank is 0.0015 square meters. Stress is force divided by area. This calculation gives us a stress of 4,220 megapascals. The problem is, high-grade spring steel has an ultimate tensile strength of around 2,000 megapascals. The stress on our plank is more than double what the material can possibly withstand. The plank would instantly and violently disintegrate, so the device would destroy itself long before it reached 10,000 RPM. But there's an even more fundamental reason why this idea doesn't work as described. The second and most fundamental reality check comes from one of the most basic laws of physics. This is Newton's third law of motion. For every action, there is an equal and opposite reaction. A system cannot lift itself using only internal forces. Think about it. The upward force we calculated on the weights is an internal force. The weights pull up on the central hub via the angled arms. But, by Newton's third law, the central hub must be pushing down on the arms with an equal and opposite force. The forces are all contained within the system of the motor and the plank. They perfectly cancel each other out. The net vertical force on the entire isolated system is zero. You can't lift yourself off the ground by pulling up on your own bootstraps. So how does anything fly? It must push against something external. A helicopter flies by pushing a large mass of air downwards. The reaction to that action is the air pushing the helicopter upwards. Our device could only generate lift if it acted as a propeller, pushing air down. Let's bring everything together and answer our initial question. Our goal was to analyze the forces on the spinning device to see if it could lift itself. We began by calculating the immense centripetal forces involved and found that, theoretically, the 30-degree angle would translate this into a vertical lift component far greater than the object's weight. However, our reality check revealed two fatal flaws. First, the material would fail catastrophically under the immense stress. Second, and more fundamentally, Newton's third law dictates that the internal forces cancel out, resulting in zero net lift for the system as a whole. So can the centrifugal forces exerted by the object on itself cause it to lift? The answer is a definitive no. While it's a creative idea, it's constrained by the fundamental laws of material science and motion. The only way for it to fly would be to act as a very, very fast propeller, pushing air down to go up. Thank you for joining this analysis.